So in this example, we'll be looking at the problem of a box moving across a floor. So we have a box is zooming across the floor to the right at Rosa. She pushes horizontally on the 200 Newton box. So she's applying a force horizontally, and the box has a weight of 200 newtons, causing the box to slow down at a rate of 3 meters per second squared. So we know the box is accelerating at 3 meters per second squared. What is the size of Rosa's force? So we need to determine what is the magnitude of Rosa's force. And we're told that we can ignore friction, so we don't need to have a frictional force in our free body diagram. So now that we've read the problem and we've highlighted the important parts, we can start with the problem solving steps. The first step is to always choose your coordinate system. So I'm going to have the positive y direction be pointing upwards, and I'm going to have the positive x direction pointing to the right. So the next step for me is I like to be able to draw just a crude picture to help me visualize things. You can do that visualization in your head, but for me, I like to draw it out. So I have a picture drawn out of this situation where there's a box that's moving to the right, so it has some velocity v to the right. The box is being pushed on by Rosa horizontally, and that horizontal force is causing an acceleration to the left, which is causing the box to slow down. So now that we have an idea of what's going on here, the next step is to choose what our object is, or what our system is for this problem. So we know we are looking for the force that's applied by Rosa, and we know that the box is accelerating as a result of this force. So since this force is being applied to the box, our box is going to be our object of interest, or it's going to be our system. So I'm going to circle that, and then I'm going to write here, box is our system. So now that we defined what our system is, we can now draw the free body diagram for our system. So over here on our coordinate system, we can draw out our forces. So the first force that I'm going to draw is the non-contact force, which is going to be the weight force. So the weight force points downwards, and that weight force is due to gravity, which is mg, but we are told what that weight force is in the problem, which is 200 newtons. So 200 newtons. Now we have to look at other forces. So we know there's an applied force by Rosa, and that force is applied horizontally. So that's going to be in the x direction. Now Rosa is pushing on the box to the left, so we're going to have an applied force by Rosa pointing in the negative x direction. So that's F Rosa. And now we need one more force that we're missing. So we know that the box isn't moving in the y direction. So the y direction, there's zero acceleration. And so if there's zero acceleration, we know that the forces must be balanced. So we have a weight force downwards. We need to have another force in the positive y direction that balances that downward force. And that force is the normal force. And that's going to be of equal magnitude to the weight force, and that normal force is being applied by the ground. So the weight force is being pulled down as a result of gravity, and then the floor is pushing upwards on the box, balancing out that weight force so that there's no acceleration in the y direction. So now I'm going to include the last bit of information about the acceleration of the box. We're told it's moving to the right, but it's slowing down. So we know that the acceleration must be to the left. And so it's going to be in the negative x direction. So we're going to have an acceleration of negative 3.0 meters per second squared. Finally, we're looking for the size of Rosa's force, or the magnitude of Rosa's force, and that's going to be F Rosa. And so since the pointing of the arrow gives us the direction, F Rosa is going to just be a positive number. And that's going to be in terms of newtons. Our next step is to plan our solution. We're only concerned with the x direction, so we're going to apply Newton's second law to the x direction. So that is the sum of the forces in the x direction equal the mass times the acceleration of the object in the x direction. The other thing we'll need is that we don't know the mass, but we do know the weight of the box. So we're going to use the weight is equal to m times the acceleration due to gravity. And so now we can execute our plan. We're going to start by finding the mass of the box because we're going to need that when we use Newton's second law. So weight is equal to mass times the acceleration due to gravity. We know the weight is equal to 200 newtons equals mass times 9.8 meters per second squared. Mass is equal to 200 newtons is kilograms meters per second squared divided by 9.8 meters per second squared. And plugging that into your calculator and we canceling units, we're left with kilograms as we expect and a mass of 20.4 kilograms. Now to find the magnitude of Rosa's force, we are going to use Newton's second law in the x direction. And so going back up to our free body diagram, we know that F Rosa, the force F Rosa, is pointing to the left. So that's going to be the negative x direction. So in the Newton's second law, we're going to have negative F Rosa is equal to the mass that we just found, 20.4 kilograms, times the acceleration in the x direction, which is negative 3.0 meters per second squared. So we have a negative on the left-hand side and a negative on the right-hand side. Those are going to offset, so that leaves us with a positive. F Rosa is equal to 61.2 kilograms meters per second squared. But if you recall, that's just equal to a newton. So we're left with F Rosa is equal to 61.2 newtons. And so whenever you're asked for the size of a force or how large a force is, you're always going to get a positive value. And the reason why is because they're asking for the magnitude of the force in both of those cases. The magnitude is always going to be positive. The direction comes in, and the direction came in here when we placed the negative sign because the force was pointing to the left. This portion here, the force of Rosa, that's going to be a positive quantity because that is our magnitude. So this is our direction. And then this part is our magnitude. And then finally, we were asked to compare this size of this force or how large this force is to compare it to problem 4. And what we found in problem 4 was it's the same magnitude. So even though we had forces in different directions and accelerations in different directions, we can still get the same magnitude of the force in the end. And so the solution's complete and the sign's positive. The answer has units of newtons for force, which is good. And then the magnitude is the same as we found before, so we're all good there.